So, hello everyone, welcome to lecture number 25. So, in the last lecture we were looking at congruent melting, the phase diagram that gives rise to congruent melting followed by spinodal decomposition. And so we started with an alpha phase which is a regular solution, a beta phase which is an ideal solution, and then so we said the Tc of alpha phase is quite low compared to the congruent melting. So, in other words, what I was saying is, if I look at this phase diagram, this is the Tc where this is the T where congruent melting happens, right. So, I can point it out to you, right. So, this is the T where congruent melting happens, that is larger, right. So, the liquid phase disappears faster or at higher temperature than where the T star, the Tc where spinodal decomposition happens. So, this is called T star, this is called Tc. Okay. So, and so this is the nature of this phase diagram, and then we said alright, congruent melting is fine, a liquid just melts as if it's a pure liquid, right. So, at that single point without really breaking up, without really solid so solute partitioning. Okay. So, without really breaking up the solvent atoms, it just so there is no change in composition at T star, or so at X star there are no various temperatures at which this melting happens. Okay. So, or this solidification happens. So, that is what we said. And then we said later on, once you start cooling it down, then there are regions where there is going to be spinodal decomposition, and in the regions where there is spinodal decomposition, the alpha phase is no longer stable, it is an unstable phase at low enough temperatures, and so it will spontaneously split up into alpha 1 and alpha 2, giving rise to some kind of periodic patterns. And conversely, if you see some kind of periodicity, you can guess that there is some spinodal decomposition at play. Okay. So, it just spontaneously the fluctuations just amplify, and then you get this spinodal decomposition. Whereas so in the other region, in this region for example, there is no spinodal decomposition, there is still so still alpha 1 plus alpha 2 is the stable phase, not alpha, but alpha is also a metastable phase, right. So, if you cool it fast enough, then you can probably stabilize it at alpha phase, right. It is not an unstable phase, it is a stable phase, it is metastable, but so thermodynamically, given enough time, given enough diffusion kinetics, it will split up into an homogeneous mixture, an inhomogeneous mixture of alpha 1 and alpha 2, and then so you do not need to expect any sort of periodicity or any sort of periodic patterns in generally the miscibility gap, where alpha itself is a stable state, right. So, there is some nucleation growth dynamics that is happening, but there is no expectation of pattern formation, right. So, if it happens so that is because of other reasons like strain and things like that we will discuss later in the later part of this course. But typically, if I see some patterns, then I can attribute so I can immediately guess that these patterns are coming because while cooling down there was some spinodal decomposition that has happened. Okay. And we said we can use this spinodal decomposition to our advantage in terms of growth of thin films, right. So, for example, in this study they were growing vanadium oxide, titanium oxide heterostructures, and the way they grew these heterostructures was through spinodal decomposition. First they would use a solid solution of titanium oxide, vanadium oxide, which will spinodally decompose at low enough temperature. So, once you cool down, it will spontaneously split up into periodic patterns of vanadium oxide and titanium oxide. Okay. And then we stopped at a stage where we said, okay, so if I am using vanadium oxide and titanium oxide, right. So, if this is vanadium oxide, this is titanium oxide, and this is grown on some kind of a substrate, and then again there is titanium oxide, there is vanadium oxide, and so on, right. This kind of a heterostructure, as it is called. Okay. Now, it is this can be grown in a growth chamber. I can use sputtering, what is called sputtering, I can use what is called pulse laser deposition, I can use MBE people typically do not use for these sort of oxides, but so I can think of using atomic layer deposition techniques and so on and so forth to actually grow this kind of a heterostructure, right. So all I need to do is I have a precursor, right. So in case of sputtering, so how does sputtering work? I have a target, right, and in this case let us say the target is titanium oxide, then so I have argon atmosphere, right. So this argon atmosphere near the magnetron gets ionized, so these argon ions go and hit the so there is something called a magnetron, right. So when I apply some kind of a bias to the magnetron, the argon ions ionize, and these argon ions are they go and hit your substrate, right. So this is like a missile going and hitting the target, right. So or a projectile going and hitting the target, and so that the target gives away a lot of debris, and this is debris of titanium oxide, okay. And this debris is typically a plasma phase, right, and then you put a substrate here, right, and everything is happening in vacuum. So I put everything under vacuum and just flow. The pressure is P argon, the pressure inside the chamber is because of partial pressure of argon and partial pressure of oxygen, since I want to grow oxide, right. So so argon ions bombard, there is the debris of the missile that comes and falls on the substrate, and on the substrate then I have a plasma too. On the substrate I have a plasma to solid reaction, followed by so once a solid is formed, the plasma, sorry, where is it, yeah, so the plasma has titanium oxide, right, so or ions of various ions, right. So it can be Ti plus, O minus, right, TiO2 minus, or whatever. So there are so many ions in this plasma. They come to the substrate, they sort of thermalize on the substrate, they move around and thermalize on the substrate and start forming these bonds again, right. So they start forming titanium oxide, so titanium oxide, whatever it is, so it forms an octahedron here, but yeah, so they start forming this titanium oxide phases and bonds, right. If you let these atoms move around, right, so the substrate should be at a temperature such that the add atoms can move around, right. So or I should give some surface diffusion. If there is surface diffusion, then I will have titanium oxide which crystallizes, right, and forms the phase of interest for us, okay. So what I can do then is I can have what is called confocal sputtering, where I have two targets, so one here, another here. This is the target of titanium oxide, this is the target of vanadium oxide. I have one substrate, right, everything is in a vacuum chamber, right. So then I can shoot argon ions to get titanium oxide like this. I can shoot argon ions or through magnetron sputtering to get vanadium oxide, and I can do them sequentially, right. So first titanium oxide, sequential growth, right. So first titanium oxide of 10 nanometers, followed by vanadium oxide of 10 nanometers, followed by titanium oxide of 10 nanometers, right. So then I can actually grow on a substrate. What I can get is titanium oxide layer, followed by vanadium oxide layer, followed by titanium oxide layer, right. So I can control, so I can make sure that the interfaces are clean, sharp, whatever, right. So and then I can study the interface physics between titanium oxide and vanadium oxide. I can make new devices at the interfaces, right, and so on. So this is possible, heterostructuring is possible, or lateral heterostructuring is sorry, this is not lateral heterostructuring in this direction, right. So heterostructuring is possible without resorting to spinodal decomposition. But this is so mostly it is one film of one layer of titanium oxide, another layer of vanadium oxide. So mostly there is a layering in this fashion, right. So it there is a heterostructure only in this direction, right. So, heterostructure out of plane. Okay. But then we then said, all right, so but then I need a device, I need a material where this is the substrate, right, and I have vanadium oxide here, titanium oxide here, vanadium oxide here, titanium oxide here. I need these the so called VANs or vertically aligned nanostructures. Okay, with these interfaces which are perpendicular to the substrate, right, and here the interfaces are perpendicular to the substrate. Okay, that way so I am interested in some kind of an in plane, I want to measure, I want to put a terminal here, put another terminal here, and then I want to measure in plane properties, right. So, in plane electrical properties. That are affected by the junction, by the interface. What can happen at the interface? At the interface, you see this is a vanadium oxide titanium oxide interface, right. So, vanadium, if I look at the atomic configuration of vanadium, vanadium has 1s2, 2s2, 2p6, 3s2, 3p6, right. Then 4s2, 3d1. Let me just think, 3d3, right. So, that is vanadium. Titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Okay. But if I have titanium 4 plus, I have 3d0, 4s0. If I have vanadium 4 plus, I have a 3d1 and 4s0. Okay. Now, at the interface, however, so I typically have titanium oxide, vanadium oxide. At the interface, so there can be this electron exchange between titanium oxide and vanadium oxide. Titanium can take off an electron from vanadium, and so it can become titanium 3 plus, and vanadium becomes vanadium 5 plus, or something like that, right. So, these sort of are in general, I mean I am just giving you an example, that is not necessary. In general, if titanium has slight number of deficiency, oxygen vacancies or something like that, titanium can give electrons to vanadium oxide. So, titanium oxide can dope vanadium oxide. Okay, this is what is called modulation doping. Okay. So, titanium oxide can give an electron, and this electron goes into vanadium oxide, and putting in electrons in vanadium oxide, it is a very interesting system that changes its properties, right. It is possible that vanadium oxide, which is insulating, can become metallic just by doping electrons. Okay. So, but I need so this is some n type titanium oxide, which means there is some extra electrons here, and these electrons can be transported from the interface to vanadium oxide, right. So, I can do all these changes to properties through interfacial transfer, and for some reason I want this change in property to happen in plane, right. So, to happen in this direction. So, the interfaces will be nice to have in this direction, right. So, not in the other direction. All these p-n junctions and so this interfacial charge transfer phenomena, I want it to happen in this direction for some reason. I do not exactly know what the reason is right now, but for some reason I want that to be my material design constraint, right. So, how can I get heterostructures where the interfaces are perpendicular to the substrate, right. So, the interfaces now should be perpendicular to the substrate. Okay. And to get those heterostructures, you cannot do typical growth, right, and in that case thermodynamics comes to your rescue. Thermodynamics and spinodal decomposition. comes to rescue, and so you can tune the strain in the system such that I get these vands, right. So, vanadium, titanium, vanadium, titanium, and so on, right. So, I get such that I get the van structures. Okay, or spinodal decomposition happens with fluctuations in this direction, right. So, this is titanium, this is vanadium, this is titanium, this is vanadium. Okay, so the periodicity can be controlled. The periodic patterns can be controlled with external strain, let us say, or other external parameters in general, not just strain, but other external parameters or other parameters. Okay. So, I'll have to do some research, I'll have to design this, but once I design, I'll start growing this and then cool it down so that the spontaneously vanadium and titanium just break down into these vertically aligned nanostructures. Okay. So, this is one way of making these vertically aligned nanostructures. There are not many other ways, by the way. So, for me to grow these nano structures with nice interfaces between vanadium oxide, titanium oxide, not just vanadium oxide, titanium oxide, any two materials, right. If I want good interfaces, right. So, between some hetero p-n junctions, right. So, hetero structures which are also p-n junctions. If I want nice interfaces in this direction, I can get it from growth, but I have to take recourse to something like spinodal decomposition. Okay. All right. So, just to give you another example, so this is again a magnesium lithium alloy, lithium aluminum alloy, and you can see so this is what is called an APT or atom probe tomography image. This is actually a 3D image of how magnesium and aluminum are, I think there is also lithium here if you see carefully, but they are in this structure, and you can see some kind of periodicity coming. This is a 3D image, right. So, you can actually rotate this needle and then get a 3D rendition of chemistry. You can see that there are some patterns, but you can actually see these patterns much more clearly in plan view, right. So, for example, here I have so blue is aluminum rich, and I do not remember what is this exactly, but there is no red here, but yeah. So there is a green and there is a blue, right. So there is a matrix, but then you have some kind of a pattern emerging, right. So pattern of magnesium in aluminum or the other way around. Okay. So emerging, and this is also a chemical, what is called a chemical spinodal, right. So you have by having a spinodal decomposition, you have separated out two different regions which have nice patterns that are formed, but these two different regions are separated by their chemical composition. So, it is called a chemical spinodal. Okay. Right. But if I see here is a region, for example, all these brown regions, this is clearly there is a pattern formed here, right, and all these brown regions, let us say this is what is called a ferroelectric material, and in all these brown regions the polarization is in a certain direction, and in all the other regions the polarization is in certain other direction, right. So, these are different domains, right, polarization domains, or you may understand magnetization, right. So, these are like patterns formed by magnetic domains, right. So, magnetic domains are oriented in different directions in different colors, right. So, they form some kind of a periodic patterns, right. So, these are what are called polarization spinodals. Okay. Now, if you have time, you go read this paper, right. So, this is an open access paper. There in fact they will divide the spinodals into polarization spinodal, chemical spinodal, strain spinodal, and so on and so forth, depending on what sort of domain patterns you form. If the patterns you form are chemically different, right. So, the alpha 1 and alpha 2 phases that we are speaking about, they are called chemical spinodals. If I still have these nice patterns that are formed, but they differ in polarizations, then that is polarization spinodal. If they differ in magnetizations, right. So, I can have up north pole facing, south pole facing in the other domain, and so on and so forth, then they are called magnetic spinodals, right. And in fact, these sort of pattern formations are what are important in today's what people call as topological patterns that evolve from these kind of spinodal structures. Okay, so it gives rise to some what are called non-trivial topologies. There is no need to discuss that in this course, but I am just mentioning it because that is a very hot research topic as the topology in space. It's called so looking at what are called skyrmions, vortices, polarization vortices, magnetization vortices, and so on and so forth. So these all these things can be envisioned under the purview of some kind of spinodal decomposition. There is a spinodal decomposition happening, and then I get this pattern formation, and these patterns have are interesting from a very physics point of view and a device perspective. Okay, to store memory, for example. Okay, so I am not going into details of it. I am just mentioning it. But if you are interested, please do read up about this, right. So this is a good paper to start, but so you can also look at now ChatGPT, ask what is racetrack memory, how can a skyrmion be used in a racetrack memory, right. So ask these questions and then try to find out yourself what these ideas are, what these novel newer ideas are, and how can you put that in a real device, and so on and so forth. Okay, so there's a lot of research happening in these fronts nowadays. Okay, so spinodal decomposition is a very important idea, and extending it not just to chemical spinodals but to polarization spinodals, magnetic spinodals actually gives you very useful devices. Okay, okay, all right. So with that, so I'll end the discussion on spinodal decomposition, and let us come to the next phase diagram. Okay. And the next phase diagram, here what I am going to do is so earlier you see, so in this phase diagram we said T star is less than Tc. That means liquid phase is not stable at Tc. Right, liquid phase completely converts to solid even before Tc. Okay. Now we are going to do the other condition. What happens if Tc is less than T star, right? Or in other words, the solid spinodal, the alpha spinodal decomposition appears even much before the liquid can completely disappear, right? So the so the condition that we are going to look at now is, okay, this brings us to our third phase diagram, and the condition I am going to look at is T star is now less than Tc, or in other words, liquid still exists in some composition ranges even when the solid, which is alpha, undergoes spinodal decomposition or miscibility gap. Okay. Okay. Now in that, so which means solid starts transforming into its spinodal at much higher temperatures than the case where liquid transforms, right. So liquid transforms into a solid. Okay. So in that case, so alpha is now flat, liquid is so at high temperatures, this is T high, liquid is below alpha. So liquid is more or less stable except at this point, that's your melting point of pure 1. Okay. Then alpha keeps coming up, the liquid starts, so liquid starts going up, alpha keeps coming down, right. But alpha also gets more and more flattened out because the entropic term is reducing, so the enthalpic term starts to dominate, and at some point the alpha splits up into alpha 1 plus alpha 2. Okay. So this is the point where spinodal decomposition has already happened, but liquid phase is still intact, right. So, at this stage, so I can do the common tangent construction, and okay, not yet, but so in the next temperature, when this is the curve, I can do the common tangent construction and then say that, look, I have the following regions here. This is alpha 1, this is alpha 1 plus liquid, this is liquid plus, this is here I have just the liquid, right, and here I have liquid plus alpha 2, and here I have alpha 2. Okay, so I can split this into 5 different stability composition regions, right. So, I have alpha 1, alpha 2, but alpha 1 plus liquid, liquid plus alpha 2, and then alpha 2, right. So, this is liquid plus alpha 2. Okay, so if that is not clear. Okay. Now, there comes a point where the liquid starts to go up, right. So, the liquid is further going up, and so between the common tangent of alpha 1 and alpha 2, the liquid can also intersect, and so beyond that the liquid is not stable anymore, right. So, beyond that the liquid has gone beyond the alpha phase, but this is the critical condition where liquid coexists with alpha 1 and alpha 2, right. Or in other words, just from above this temperature to below this temperature, right. So, so if I am at this composition, I have a liquid first, right. So, just below this temperature, that liquid becomes alpha 1 plus alpha 2. Okay. So, here is now I can plot everything in the form of this phase diagram, right, and in this phase diagram, this is what is called a eutectic phase diagram, where at high temperatures I have liquid that is stable. Liquid first transforms into the alpha 1 phase here, it transforms into the alpha 2 phase here. This is the pure compositions, but the impure compositions start giving both alpha 1 plus liquid initially and alpha 2 plus liquid on this side, okay, this composition side, right. Now, at some point this liquid completely disappears and it forms a total alpha 1 plus alpha 2, right. So, here the liquid here disappears and forms the alpha 1. Alpha 1 plus alpha 2, and liquid here also disappears and forms alpha 1 plus alpha 2. So, what I have is a material now which is inhomogeneously split up into alpha 1 and alpha 2 phases, right, and this point where liquid 3 phases coexist at this point and liquid gives rise to alpha 1 plus alpha 2, this is called the eutectic point. But now you can understand that the eutectic comes again by thinking of a regular solution. The simplest way to derive a eutectic is to think of regular solution for alpha, ideal solution for liquid, and the fact that T star or liquid is even stable, T star is less than T star is where liquid completely disappears, right, is less than Tc. Tc is the spinodal decomposition, right. So, if this alpha is splitting up into alpha 1 plus alpha 2, I have a spinodal decomposition, right. So, this is one way of getting a binary eutectic phase diagram. Okay. So, that is our phase diagram number 3, right. So, so you get what is called a binary eutectic, right. So, where I have this is temperature, this is composition xb or x2, right. So, I have an alpha phase, I have an alpha 2 phase, this is liquid, right, and this at this point I have liquid gives alpha 1 plus alpha 2. Okay. This happened when alpha is regular, liquid is ideal, and T star is the point where liquid completely disappears is less than Tc. Tc is the point of spinodal decomposition of alpha into alpha 1 plus alpha 2. Okay. At Tc, alpha becomes alpha 1 plus alpha 2. Okay. You can just follow the slide that I showed and you can understand in detail how this phase diagram is formed. Whereas if T star is greater than Tc, then we have liquid gives rise to alpha. This is just a congruent melting problem, right. If T star is less than Tc, I have a binary eutectic. Okay. All right, very good. Now, okay, so that is I take one phase and I am saying that this phase is going to split one solid phase, and I am saying that at below certain temperature this phase is going to split up into two different phases, right. So, instead I can actually start with two different phases, alpha and beta, right. So, two different solid phases and one liquid, okay. Both of them regular solutions again. So, alpha is like this, beta is like this, right, and then here also I can first at T greater than Tm1, which is the melting point of component 1, alpha and beta are not stable, liquid is a stable phase, alpha and beta are metastable. Once I reduce the temperature, so alpha gets some stability, beta is yet to get some stability. So, I will have a region where I have liquid plus alpha here. I have a region where I have liquid plus alpha, I have a region, this is all liquid, this is all alpha. Okay, so alpha starts to nucleate from the liquid, right. So, then at this temperature, at the melting temperature of T2 or Tm2, beta starts to nucleate, right. So, then I have a region again, this is alpha, liquid plus alpha, liquid, but beta is just starting to nucleate. Right. So, only it exists only at this point, right, and here again I can draw the phase coexistence through common tangents, right. So, the exercise that we did earlier. So, again this is alpha, liquid plus alpha, liquid plus beta, and this is beta, and then so the liquid line goes up enough that it falls on the common tangent between alpha and beta, and that is where I have liquid transforming to alpha plus beta, right. So, that eutectic reaction comes up again, and I can combine all these things and draw it in the form of this phase diagram. You can see that at the eutectic point, liquid transforms to alpha plus beta, not necessarily alpha 1 plus alpha 2. So, here it is not necessary that I start with an alpha phase which has which is a regular solution and which spinodally decomposes into alpha plus beta, alpha 1 plus alpha 2, but I can rather start with two phases, two solid phases, alpha and beta, which can be ideal, which can be regular, does not matter, right. So, I don't rely on the fact that they have to decompose, okay, one phase has to decompose, right. So, if I have three phases in my problem, then also I can construct these eutectic reactions, I can construct these binary eutectic diagrams, and so at this point, right. So, of the phase diagram, this is my phase diagram number 4, right. So, at this point on the phase diagram I have a eutectic reaction, liquid gives rise to alpha plus beta, and so this is a 3-phase coexistence region, and according to phase rule this is the maximum number of phases I can have at any given point, right. So, 3-phase coexistence is the maximum, which is the maximum number of phases at any given point, right. Now, if you compare the eutectic point compared to Tm1 and Tm2, right, eutectic, so liquid exists until here and liquid suddenly disappears into a solid state, right. Here also liquid exists until here, this is pure compound, and liquid disappears into a solid state. Here also liquid exists until here and liquid disappears into a solid state, right. But this temperature is less than both these temperatures, right. So, that is the advantage of using what is called eutectic alloys. This is in general used to reduce the melting point of alloys or materials, right. So, at the eutectic point I have the minimum melting point, and so so I can do processing at lower temperatures, I can heat and cool at lower temperatures, right. So, at the eutectic or rather eutectic alloys show reduction in melting point compared to other alloys, okay, at the eutectic point. Non-eutectic alloys or pure elements, right, at the eutectic point, right. So, how can we use it? We can use it to do some low temperature processing, right, and the classic alloy is lead tin alloy, and lead tin alloy is called solder, right. This is a eutectic alloy. I have a eutectic point, right. So, this is probably lead, this is tin, and I have a eutectic point. So, and this is I do not remember the exact temperature, but this temperature can be reached using a solder gun, right. Otherwise, if I have to melt lead or melt tin, these are actually high melting point alloys, right. So, if I start heating them to 700-800 degrees Celsius on an interconnect, right. So, I want to make some connections on a PCB, on a printed circuit board, which is called the PCB. I want to make some make some connections, right. I will put a resistor which is going to be an element like this, and I want to solder it there. I want to fix it there, electrically fix it to some kind of a line that already exists, right. So, and so on, right. So, I want to put a transistor, right. So, this is a resistor. I want to put a transistor, and then so transistor and then solder it, or so put it on my PCB, right. So, what am I going to do? I am going to solder, right. And so since this is a plastic board with already lot of other connections that are there, right. So, you may have seen a PCB, right. So, I do not have it in my hand right now for me to show you, but everyone would have seen a PCB by now. Otherwise, please take a look at it, right. So, this is a plastic board. So, heating it up to 1000 degrees Celsius or 700 degrees Celsius is that is a hard, so I will start destroying the plastic, right. So, rather I want to heat it to as low temperature as possible. So, I would use this eutectic alloy of lead and tin, and that is called the solder alloy, right. And solder alloy has a melting point much lower, where this PCB is safe. I forget the exact temperature, I can tell you in a while. So, where the PCB is safe, and so I can just use that solder iron, and then put the contacts of lead and tin. Lead and tin is a metal again, right. So, I can put these contacts wherever I want. Okay. So, so eutectics are used, the idea of eutectic is used in this soldering business. Or so the reason why soldering works is because lead tin or solder alloy works is because that lead tin alloy has a eutectic point, right. So, the liquid then goes to directly lead rich phase plus a tin rich phase, right. So, that is my, once it melts, right. So, I do not have a, so once the liquid solidifies, it completely solidifies, right. It is not like so if I have any other phase diagram, right. So, this is liquid plus alpha, this is alpha, right. So, this is an isomorphous phase diagram. If I use this for soldering, right. So, I start cooling the liquid down. So, first the liquid is there, right. So, I liquid of some metal is there, right, and then part of it is solidified, the part of it starts flowing, right. So, there is a mess. It makes a mess, right. So, I want to just put my liquid there and completely cool it, right. So, in this region, right. But if the liquid starts to flow and other things, right. So, because the solidification is not an abrupt solidification, it does not happen as liquid gives rise to alpha 1 plus alpha 2 or liquid gives rise to alpha plus beta, but it happens slowly like here, right. So, over a range of temperatures liquid is converting to alpha, then so this liquid spreads over, and so I make a mess, okay. So, it is better, it is hence safe to use eutectics, and also the added advantage of eutectics is I have a lower melting point, compared to pure metals or pure elements, right. So, I can do this processing at a lower melting point, and then liquid, so once it cools below Tm just becomes alpha plus beta, or lead plus tin or something like that. Okay. So, I have a nice bond and a nice conducting bond that I just make at the leg of the transistor and the PCB, right. So, this is the leg of the transistor and this is the PCB. Okay. So, that is where I use it. Okay. So, that is one of the examples, and in the next class we will start with another example of eutectic, right. So, and this time we are going to see how to grow nanowires by taking advantage of eutectic phase diagram. Okay. So, that is the case study we will look at for eutectic phase diagram, and then move on to a couple of other phase diagrams of interest, right. So, in the next class. Okay. So, and by the end of that, so we should understand how to read phase diagrams, right. So, we do not get perturbed by looking at phase diagrams, but all these phase diagrams, I look at them and then I can think of some process, right. So, process to make a material like spinodal I have seen, and then I have made a process to make these vans. Okay. Well, eutectic I have seen, and I have thought of an alloy which is eutectic that can be used in electronics industry just for soldering, right. So, at low temperature melt and immediately make the bond, right. So, soldering should actually make the bond, right. So, between the new transistor I am punching into the PCB and the PCB itself. Okay. And so, PCB should be safe, I should do it at low temperature. So, eutectic is the phase diagram that comes to my rescue. Okay. So, in the next class we are going to see another advantage of this eutectic, right. So, the isomorphous phase diagrams, or it does not need to be isomorphous, but so first we started by using this phase diagrams for zone refinement, right. So, purifying materials, right. So, there is a lot of technology that just came out of looking at phase diagrams. Okay. So, we will look at another case study in the next class. Okay. All right, I will see you again in the next class. Thank you very much.